It's asking about concavity. Do you know what you need to find to get that?
We find like the derivatives
Which derivative?
for the second one.
Yeah. Concavity has to do with the second derivative. Okay. Do you know what the derivative rule for ln is?
I know it's like 1 over f.
Okay. Yeah. And then, so for this kind of function, do you know what rule you'd have to apply overall?
The chain rule.
Yeah, chain rule, right. Okay, so how would that work here?
Is it like the 1 over x squared plus 16?
Okay, that's the first part. What else does the chain rule say you need to do?
Oh, times it by like the derivative or something? The actual derivative of x squared plus 16?
Yeah, derivative of the inner function, right? It's typically the derivative of the outer function, which is the 1 over part for the ln. The outer function's ln, right? So you do 1 over whatever the inner function is, then derivative of the inner function, right? Which is what?
2 of x.
2x, yeah. So put that on top. Okay. All right, so that's the first derivative. Then what's next?
You have to take the second, you have to find like derivative of that one.
Okay.
Oh wait, do you use the quotient one? Quotient
Yeah,
rule?
exactly. Quotient rule because it's a function over function.
So if you're going across, it would just be 2. Then it would be 2x. So it's x squared plus 16 times 2 minus 2x times 2x over the x squared plus 16 squared.
Yeah. Okay. Yeah, what do you do with this?
You have to set it equal to 0, right?
Yeah, you can set it equal to 0. The second derivative is equal to 0. What does that mean? What's it called when the second derivative of a function is 0? What are those points called?
The zeros.
So those are what the inflection points are. Inflection points are what the second derivative equals 0. If you look at the graph of the original function, the inflection points are when the function, the slope changes from increasing to decreasing or decreasing to increasing. So
Yeah.
it looks something like this. This is what an inflection point looks like because you see how the slope gets flatter as you
Yeah, like
approach.
yeah.
And then right after the inflection point, it gets steeper. So that's what it looks like, or it might look something like that. So it just changes steepness. That's kind of the way to think about it. It goes from
Okay.
flat to steep or steep to flat. Okay, so then he said equals 0. So how do you solve this then?
I don't know. Like, do you do like the top and bottom or?
Well, so it's a fraction, right? What's nice is since it's set equal to 0, what can you do to both sides first, or how do you get rid of the fraction?
You times it by the denominator,
Yeah,
so that they
exactly.
cancel out.
Right. So then what's the next line look like?
Then it's the x squared plus 16 times 2 minus 2x times 2x equals the x squared plus 16 squared.
Well, what happens if you multiply that to 0?
Oh, it's just 0? Oh.
Yeah, that should make sense, right? Because remember, with fractions, 0 over anything is just equal to 0, right? So the denominator
Yeah.
is not relevant in this equation. Okay, so then what's next?
Simplify the ones here, like times it out.
Okay, what do you get?
2x squared plus 32. Negative 4x squared.
Okay,
Or do you just combine those?
yeah,
Oh, and it's negative 2x squared.
okay.
So it's negative 2x squared plus 32.
Okay, what's next?
You can factor it's negative 2 times x plus 4 times x minus 4.
Yeah, factor out -2, you get x squared minus 16, x plus 4, x minus 4. Okay,
And then What was the question again?
You'll
Oh,
find when the function's concave up, concave down, and inflection points, first of all, of x. What's x equal to?
-4 and 4.
Okay, and what do these tell us?
So like the x point of the inflection points.
Yeah, exactly. These are the x coordinates of the inflection points, or they tell you where the inflection points are.
And
Okay, so then we know where the inflection points are. And do you know what it means when a function's concave up or concave down? Well, what does the second derivative have to be in order for the function to be concave up?
is it like a positive?
Yeah, concave up means second derivative is positive, and then opposite concave down is second derivative is negative. So do you know how to find when that occurs? We can set up a number line, right? Because inflection points are the boundaries, or yeah, they separate the number line into intervals where the function's either all concave up throughout that whole interval or concave down throughout. So we know that second derivative is 0 here.
Yes. Just
So
find
then,
like the point that's in between them and you plug it in to see like
yeah,
what the sign is.
okay, yeah, okay. The first number you want to
Like
check.
-5
Okay, -5. Where can you plug that in?
to the ln x squared plus 16.
Well, if you plug it into the original function, you'd get the y coordinate of -5.
So then the derivative.
Well, the first derivative will tell you whether the slope is positive or negative, or whether the function's increasing or decreasing.
So then the -2x squared plus 32.
Yeah, we want to plug in the second derivative, right? Because we're dealing with concavity.
Mhm.
Okay, so second derivative, that simplifies to, yeah, I guess you can plug it in either here or here. Typically, you want to plug it in the factored form, just then you can see what the signs of the separate factors are. But yeah, this one's okay as well. Okay, so then if you plug it in, -5 in, what's the sign going to be?
Negative.
See, so negative, right? It's negative, plug in negative, negative. Yeah, 3 negatives overall is negative. Okay. What about in between?
Gives you 0. So
Okay.
32. So it's positive.
0, right? Positive, negative, negative gives you positive. Okay. Then what about?
And just 5.
Yeah.
So it's negative.
Yeah. Positive, 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 negatives gives you negative overall. Okay. So then what can you conclude? Reflection points are when the second derivative is 0.
Okay.
So that's what we found. So that when we set the second derivative equal to 0, these are the x values we found,
Oh,
right?
this is like where the concave downwards and the upwards and downwards.
Yeah. So let's go through each part. Where's the function concave up?
Between -4 and 4.
Okay, yeah. Part is concave up. And where's the function concave down?
Negative infinity, -4, and then 4 infinity.
Okay, and then where are the inflection points?
-4 and 4.
Yeah, exactly. Okay, does that make sense?
Yeah.